short case study on descriptive statistics today, just very short. This is just a recap then from what we just heard. So descriptive statistics means using empirical methods to describe populations. And we are going to be arranging data, displaying data, and we talked about histograms, we talked about box and whisker plots, and we talked also about calculating parameters like the mean, like the standard deviation, like the variance and the range. We also looked at, for example, this is the example of the histograms. So you can see then the histogram is a frequency distribution where you look at how many times a certain data point has occurred or a certain range of data points have occurred, and you plot them in a bar graph, and then you can see where the most data is appearing. You can also have a cumulative graph, which means that you're starting with the lowest possible value that you can have, or the lowest possible range, and you are then accumulating the points up until a maximum point. And these two types of graphs are used then very, very extensively in data analysis and data presentation to show the data that you've collected. We also looked carefully at a very, very powerful and useful type of plot called the box and whisker plot. And this is my favorite one. Here, it has all the information, well, more information than you have from the histogram, but you see it in a very concise way. The small box tells you roughly how wide your distribution is. It gives you the median value, the x50, and the minimum, and then the maximum value, x0 and x100. And then you can have the percentiles, x25 and x75, to show you where the bulk of your data is situated. So looking at the width of this box gives you an idea of how spread out your data is, as of course does the minimum and the maximum value. So what we want to do now, we want to show you a case study from our textbook, and we want to show you how you can use the histogram and the box and whisker plot, and how you would start to look at this data. So this is a case study about a foundry, an iron foundry which makes very, very large castings. So if you know nothing about iron foundries and castings, this is exactly what I want you to feel right now. You are the quality engineer. You are taking the tools that you have learned and you are going to apply them then in a setting where you are not the expert. How can you use your knowledge to help improve a process? So we will tell you though, in this foundry, molten iron is carried from a furnace where it's heated to very, very high temperatures. It's melted iron. It's then carried about a distance of 150 yards through the factory to where it is then poured into the molds to make the castings. So this is the information you're given. You have molten iron from a furnace traveling through the factory at about 150 yards, and then it's poured into the castings. Now, you have a few parameters that you have to get from the people in the factory. And the first information you have is that the process engineer has estimated that the temperature from the tapping out, from when the molten iron is taken from the hot furnace, it drops. The temperature drops about 20 degrees Fahrenheit. And when it's finally poured, it's 20 degrees cooler. 20 degrees Fahrenheit cooler. You also have a target temperature. For this pouring, the target temperature is 2,550 degrees Fahrenheit. That's your target. Is that clear for everybody? Okay. Then, the problem is, the customer gets the final castings and has burn-in defects. And what they've attributed these burn-in defects to is that the pouring temperature is too hot. And everything that has burn-in defects has to be scrapped. It's not acceptable quality. So, quality engineer, what are you going to do? Well, of course, you're here to measure data. You can measure the temperature where the molten iron is tapped out, and you can measure the temperature at which the molten iron is poured. So let's look at the pouring temperature. Now here you see a histogram, and here what we've marked is the target temperature. So note again, the target temperature is 2,550 degrees Fahrenheit. And we estimate that then there's a cooling of 20 degrees before it gets to that point. Now what you can see also on this graph is a upper spec limit and a lower spec limit. So beyond the upper spec limit, the temperature is too hot. And that's what I have indicated here on the slide. Above the upper spec limit, you get burn-in defects. And this part of the castings, this amount of castings are not usable. You may also here notice that this looks like just one distribution with one peak. You have some values that are a little bit low. But you can also notice one more thing. Is your distribution centered around the target? Without doing any calculations, do you see that your distribution of temperatures is centered around 2,550? I think you can see from here the answer is no. The question is, where is it centered, and what does that mean for your quality improvement? So, roughly speaking, it looks about 10 degrees higher than target. Instead of 2,550, you're centered closer to 2,560. So, that should indicate to you that the estimation of a 20 degrees drop is incorrect. But we'll come back to that later. The other last important thing, if you look between the lower spec limit and the upper spec limit, you have about 60 degrees difference between the spec limits. But this pouring temperature, in the total range of this pouring temperature, is higher than 60 degrees. It's more like 100 degrees. So again, from this descriptive data, from this histogram, you can see at what temperature about what temperature you're pouring out and what is the range of your data without doing any calculations. This is the heart of the descriptive statistics. But what should you do? So let's go one more slide forward and we get to the tap out temperature. Now here we see the data that we've collected from when the iron is actually molten and when it's taken out. Now, again, we had targeted 2,570 degrees Fahrenheit so that after the traveling through the 150 yards traveling, it would be at the target of 2,550. But what do you see with this data? What can you see with this data now? Where is this data centered? And if you look, again, without doing calculations, it's roughly centered around 2,570, which is what we wanted. And the scale here is different. If you take the entire range, it's about 60 degrees. So actually, your tap-out temperature is not bad. It's centered where you wanted it to be, and it's maybe a bit too large, but it's 60 degrees range. So now you have to think, what are you going to do? How can you bring your pouring temperature down 10 degrees? And how can you reduce the variability? So let's first, though, before we come to that, let's look at the box and whisker plot, because those diagrams told us a lot of information. But here, with the box and whisker plot, we have all that information in a very compact, concise way. And you can see for the tap-out temperature, we have a higher, a median temperature, 2,570, and for the pouring, we're at 2,560. That's not our target, that's too high. You can also see that the spread of the data increases slightly at the pouring temperature. So, just to summarize our data one more time. The tap-out temperature is too high. We're getting burn-in defects due to too high pouring temperature. The tap-out temperature is centered at about 2,570 degrees Fahrenheit with a range of about 60 degrees Fahrenheit. Once this molten metal travels, it comes to the pouring out phase, and it's also too high. It's centered at 2,560 degrees, which means that this initial estimation of 20 degrees drop is too high. It should be more like 10 degrees. And so that's the first thing that's wrong. What are we going to do? We're going to adjust the tap-out temperature here by 10 degrees lower. Then when it drops 10 degrees, we will pour it out at the target temperature of 2,550. That's to bring your process to target. Then the next thing you need to do is to think about reducing the variability. Now, how could you do that? Now here you, as a quality engineer, you need to talk to the people. You need to work with the factory. How much is it costing to you to scrap these parts that have the burnout defects? What will it bring you? What could you do? And some ideas might be you could somehow shorten the distance between the tap-out temperature and where you're actually doing the pouring. Could you change the container? These are the things that then is the next step in your quality process. But having these descriptive statistics means you've looked at the data, you've done the analysis, and you're able to explain to the company, to the colleagues, to the entire factory what is wrong and how it could be improved. So, thank you very much.